Okay, here's Trig lecture 117 through 120. That's 4 days. Student will use vectors to solve problems involving force and velocity. We'll talk about what vectors are in just a second. But before we get started, I want to give you a little walk down memory lane, talking about transversals. And if we have two lines that are parallel to each other, these two lines, or line segments rather, appear to be running east and west. If they're cut by another line, we call the transversal, then alternate interior angles are congruent. We're going to be using that fact today. Other angles are also congruent, but we're going to be seeing cases where we're going to need to use the alternate interior angles. So all lines that run east and west are parallel to one another. Similarly, all lines that run north and south are also parallel to each other. If we have two north and south lines that are cut by a transversal, then alternate interior angles are congruent. We're going to run into that today, both of those situations. With that in mind, let's see if I can get this board to work, and we will talk about vectors. First of all, a vector is a directed line segment. Directed just means it's going to have an indicated direction that a force of some sort is going to be moving, or a velocity. And a directed line segment that has two characteristics, direction and magnitude. And magnitude is, we're just going to think of that as the length of the segment, okay? The length of the vector. You can think of the magnitude as the length of the line segment, which is the vector. Okay, the vector is a line segment that has direction and length, magnitude. So here we go. We're going to be adding vectors together, and when we do this graphically, we're going to use what's called the tip-to-tail method, and I'll try to illustrate that here in just a second. The sum of two vectors is called a resultant, and I'll show you how to find that graphically. There are algebraic approaches, but we're going to be doing it graphically. And here's an example. We're going to add the following vectors using the tip-to-tail method, and we're going to find the resultant. We're just going to sketch the resultant. Let's see if I can get my board to work here. Yay! Here we go. If this works, I'll be very happy. I've had trouble with this board. Let's see if I can get it to work. Example, add the following vectors, find the resultant of the vectors. To add them tip-to-tail, think of it as the tip of an arrow. This force is moving in this direction, and the magnitude is that long. Magnitude is the length. This is moving in this direction, and that's the magnitude of the vector. To add them together, we go like this. We go tip to tail, graphically. Doesn't matter which tip we go to which tail. What matters is we go the tail of one of them to the tip of the other. Here's the tip of this vector. Here's the tip of this vector. We went the tail to the tip. The tip of it is the arrow. And the resultant, let's see if I can do this in red. We'll see. The result will be this vector right here. It didn't do it in red. Don't ask me why it didn't. But that's the result. Now it's going to switch colors on me. This board is kind of, it switches colors for no reason at all. I'm just going to plow on through it. I haven't been able to figure out how to stop it, so we're just going to keep going. This is the resultant vector. R is what I called it, and that little symbol there, it looks like that just means vector, the word vector. And this is what we get if we add these two vectors together using the tip-to-tail method. This is the resultant graphically. With that in mind, let's take a look at some things here. The direction of a vector can be communicated in many ways. We're going to be doing it the way I'm about to illustrate. We'll be determining direction as follows. Sketch a vector with a given direction and magnitude. So here we go. Our direction is north 30 degrees west. I'll show you what that means in just a second. 500 miles an hour. If I were going to just sketch this, I'd say, well, north is going to go this way. 30 degrees west will be 30 degrees to the west. So I'm going to set up a north, south, east, west down here. North, south, east, west. Hey, look, it changed colors again. There's north, south, east, west. You don't have to put in the NSW. You don't have to put these letters in there. I'm just saying that's north, south, east, and west. And if I'm going to go north 30 degrees west, well, due north, I'm going to put the tail of my vector right here at what you could consider the origin. And then I'm going to go due north and rotate the vector 30 degrees to the west. So it would look something like this. So where this is a 30-degree angle right here between due north, change colors again, between due north and the vector itself is 30 degrees, that angle right there. North, 30 degrees west. And to label the magnitude, I'm just going to call it 500. That's 500 miles an hour. This vector represents 500 miles an hour. Hey, it's changed color again. How about that? Why it does that, we may never know. I wish it would stop. I have no idea how to make it stop. So let's take a look at that. If that was 500 miles an hour, then half of that would be 250. 1/5 of it would be 100 miles an hour. 100 miles an hour would be that long. We try to stay fairly consistent when we're sketching. We're going to be sketching by hand, so we're not going to expect perfection, but that's an idea of what north 30 degrees west, 500 miles an hour might look like. Let's take a look at this one. South 40 degrees west, 2,000 newtons. Well, since I'm going to be moving south, I'll put my north, south, east, west here. And I'm going to go south 40 degrees to the west. West is this way, okay? So that'd be about like this. And this angle right here would be 40 degrees. I rotated, there's the tip of my, the tail of my vector. Here's the tip of it. I rotated 40 degrees and I'm going to label it 2,000 newtons. That's the magnitude of the vector. Newtons is a unit of it's a force, I'm sorry. So if that's 2,000, then half of that would be 1,000, so forth and so on. So we're just graphing what vectors, giving us an idea of how to do direction and magnitude. Here we're going to go north 70 degrees east, so I'll put my north, south, east, west down here. If I go north 70 degrees east, here's the tail of my vector. I'm going to rotate 70 degrees east. It would look something like this. And if I rotate 70 degrees east, I know that this right here would have to be 20 because 70 plus 20 is 90, and north, south, east, and west, they intersect each other at 90 degrees. So if I needed it, that angle right there is 20 degrees. However, I'm just indicating the direction and the magnitude. That's 200 pounds. If this is 200 pounds, this vector right here, half of it would be 100 pounds, 1/4 of it would be 50 pounds, so forth and so on. Okay, and let's take a look at another one. Here I've got south 38 degrees east. So I've got north, south, east, west right here. And I'm going to go south 38 degrees to the east. So that would be about like that, roughly. And we could call that 600 kilograms. This would be 38 degrees right here. And this one here would be 52 degrees if I needed it. And I would label that 600 kilograms. I apologize for this thing changing colors. Again, I wish I could stop it. I have no idea how to stop it. It's a brand new board and it's very frustrating. However, patience, perseverance, we'll figure it out one way or the other. But right now, there we go. Onward through the fog. Sketch the sum of the indicated vectors, tip to tail. So I've got this vector and this vector, u, vector v, and vector u. I'm going to put them both on the same north, south, east, and west and see what they look like. I'm going to start with south 20 degrees east, and then I'm going to go south 80 degrees east. So I'll start right here. There's north, south, east, west. If I go south 20 degrees east, it'd be something like this, and this is 30 newtons and this is 100 newtons. So this one's going to be a little more than 3 times the length of that one in my sketch. It's not going to be perfect, but I want to try to make it fairly close. So if I call this 30 newtons from here to here, whoop, and this is 20 degrees east, so this angle right here would be 20 degrees right there. I know that that angle right there is 70 degrees if I needed it from here to here. I'm going to call this 30 newtons. 30 newtons. is the length of that vector, right there. And then from the tip of this one, I'm going to add this vector. So I'm going to go north, south, east, west. And I'm going to go, now look here, this is, right there, this is a 20-degree angle. Now this is north-south, this is north-south, so this is a 20-degree angle also, right here. This angle and this angle are both 20 degrees. So these are alternate interior angles, so if I need that, I'll have it. I'm going to go south 80 degrees east, south 80 degrees east. So that would be about like this, roughly. And that would be 100, so this is 3, that would actually have to be longer to be kind of in the ballpark. Yeah, that's close enough. And this is, if this is 80 degrees, uh-oh, my board is just intent on giving an old man problems today. If this right here is a rotation of 80 degrees, then I know this is 10 degrees. If this is 20 degrees right here, as we said earlier, then this one has to be 20 degrees, right there. And 20 plus 90 plus 10, that's 120. So this angle right here, if I need it, is 120 degrees. It's kind of messy. And I want to draw, see, that's 100 newtons. I want to draw the resultant. The resultant would be this right here, from the tail of this one to the tip of that one. And notice that it forms a triangle. This is a triangle, 120 degrees. I know this side is 30 newtons. I know this side is 100 newtons. I could figure out the length of that using the law of cosines. I can find the length of the resultant, and I can find out the direction just by figuring out all these angles and saying, well, I'm going to have to find that angle and add 20 to it. And that would be south 20 plus alpha degrees. But there's a sketch of angle vector v plus vector u. This is vector v, the first one that I drew. And the second one is vector u. That little symbol right there just means vector. Okay, let's move onward through the fog and do one problem. And I'm going to get rid of this real quick. I should probably leave that up there. That's a pretty nice drawing. In fact, I think I will. I'll just talk through it. That will save us some headaches. A plane leaves an airport traveling north 40 degrees east. So here's where I'm leaving from. North 40 degrees east. That's the plane right there. Oops. Oh, my poor board is not going to help me at all. There we go. It's not the poor board, it's just a brand new board, and I have no idea how to work the cotton picking thing. My old board worked much better. The plane leaves an airport going north, 40 degrees east, and it's going 200 miles an hour. So I called that 200 miles an hour. The length of this is 200 miles an hour. It's the length of the vector, the magnitude of the vector. And then the wind is blowing south 60 degrees east. So from here I added the wind vector to the airplane's velocity vector. And what I wound up with was south 60 degrees east. So this is 60 degrees right here. And it's going 50 miles an hour. That's the wind. So my resultant vector goes from the tail of the original to the tip of the wind, and that will give me the resultant vector of the actual speed and direction that the airplane is flying. Here's where it would be flying in still air, but the 50 mile an hour wind comes into play. It's made the vector a little bit longer, so the plane is sped up, and it's changed the direction a little bit. It's, instead of having a direction of north 40 degrees, it's now north 40 degrees plus alpha. So I'm going to find alpha, add that to 40, that'll be my new direction, north 40 plus alpha degrees east. And my new magnitude I'm going to find using the law of cosines. So here we go, I'll find the magnitude first. I'll say r squared is equal to 50 squared plus 200 squared. This is the law of cosines that we did before. 50 squared plus 200 squared minus 2 times 50 times 200 times the cosine of, let's see, if this is 40, these two lines are parallel. If that's 40, that's 40 also. And if this is a rotation of 60, this angle right here is 100 degrees. This angle right here is 100 degrees, so I'm going to call it 100 degrees. Cosine of 100 degrees. And I'm going to see if I can get rid of that little box. And maybe I can, maybe I can't. There we go. So this is the law of cosines. It will give me r. If I plug all this in and then take the square root of it, r will equal approximately, should be a little bit more than 200. I did it earlier, so I'll just go ahead and, instead of standing here and doing it with my calculator and boring you to tears, I got 214.4, and I checked that and it's correct. That's rounded to the nearest 10. Notice that the speed of the airplane, this was original speed of 200 miles an hour. The wind comes into play. Now the airplane is traveling 214.4 miles an hour. And it's changed direction. So I want to find alpha. That's that angle right there, and add it to 40, and that'll give me the new direction. It'll be north, 40 plus alpha degrees east. So I'm going to find alpha using the law of sines. I'm going to say 50 is to the sine of alpha. That's 214.4 is to the sine of 200. 50 is to the sine of alpha as 214.4 is to the sine of 100. And rather than bore you with the algebra and everything, I'm going to cross multiply, solve it for the sine of theta, and then take the inverse sine of both sides, and I'll get alpha is equal to about 13 degrees, if I remember correctly. Yeah, 13.3 degrees, using a little bit of algebra there. Now, if alpha is 13.3 degrees, then this rotation is 40 plus 13.3. So this rotation right here, that's 53. 40 plus alpha is 53.3 degrees. So if I was going to state my new direction and my new magnitude, I would say it's going to be north 40 plus 13.3, so that'd be 53.3 degrees to the east. And my new magnitude, the speed of my aircraft, would be 214.4 miles per hour. So it's increased the speed from 200 to 214.4. The wind has done that. This 50-mile-an-hour wind blowing in this direction. It's increased the speed, and it's changed the direction from north 40 degrees east to north 53.3 degrees east. So that's a significant little change there by a 50-mile-per-hour prevailing wind. That's the type of problems we're going to be doing over the next few days. I will be happy to help you with any of them. We can do Zoom, or you can come to class. However, I don't even know if we're going to be in class, but you can do this.